Well, just like any other problem, such as semantic parsing, constituency parsing, and dependency parsing, all of them can be categorized to, for example, graph-based algorithm and shift-reduced algorithm. And shift-reduced are two types. Either you go from bottom-up or top-to-bottom, and bottom-up. And the third could be just sequence to sequence, seeing the problem as a machine translation problem. So it's sequence to sequence. Oh, I've seen an article in 2022, which is in the fourth category, which is they see parsing as tagging. Parsing is tagging, and for example, we say this one is -1 relationship with this head. It means that if you go one token to the left, then that is your head. If you go, for example, 3 tokens to the left, that is your head. This is the fourth, which is not very popular, but most of the algorithm are graph-based algorithm, but they suffer from CKY algorithm. So first they create a score, like the one that we will create today, and they suffer from CKY algorithm because it's a polynomial algorithm. The computational complexity is a lot in comparison to shift reduce, which is very fast, also it is not robust. By robustness, I mean that it is not robust, I mean that it may not always come to the global solution. But it is very fast because it doesn't need any CKY for inference. It's very fast. As soon as you find the next action, then you can incrementally create your parse, and that's fine. And sequence to sequence, they are popular in semantic parsing. For example, in semantic parsing, we translate your natural language, we convert it to, for example, to a SQL or to a SparkQL if you're working with knowledge graphs. So they use sequence to sequence. So all of these paradigms can be used not only for dependency parsing, but also for semantic parsing, but also for constituency parsing, discourse parsing, and any kind of parsing that needs structured prediction. So let's focus on this article, on today's article, which is Deep Biaffine Attention for Neural Dependency. Of course, it is inspired by this article from great people in Israel, and so each head has a label and relation to its dependent, and each dependent has a label and a relation to its head. This is in what we do in dependency parsing. So the contribution of these great people, from Christopher Manning, my favorite researcher, so the contribution is that we build a network that's larger but uses more regularization. We replace the traditional multilayer perceptron. In the previous lecture, in this article, they used MLP, but now they use a biaffine one. So rather than using the top recurrent states of LSTM in the biaffine transformations, we put through multilayer perceptron. So it reduces the dimensionality. So a dependency parsing, a transition-based approach could be like this. At each step, the feed-forward neural network assigns a probability to each action. For example, saying that going left, going shift or reduce. Shift or reduce. Reduce could be, for example, going left or right. So this is the standard way that we do for a transition-based approach. So we assign a probability to each action the parser can take based on the word, part of speech tag, and label embeddings. A graph-based approach could be seen in this paper, Goldberg's model. The bidirectional LSTM output vector for each word is concatenated with each possible head's recurrent vector, and the result is used as an MLP that scores each resulting. Once we know that these resulting arc scores, then we are good to go, and we can predict the global tree using CKY algorithm for inference. We can use CKY algorithm, but it is good to use. It is good to know that CKY has its own problems because it takes time. It's not as fast as shift-reduce algorithms. So graph-based algorithms are usually not as fast as shift-reduce algorithms, which are transient-based approaches. So the predicted tree structure at the training time is the one where each word depends on its highest scoring head. And labels are generated analogously with each word's recurrent output vector and its goal or predicted head word's recurrent vector being used in a multi-class, multi-layer perceptron. So this is really interesting because you're using this recurrent neural network, and for each word, for each token, it could be both arc dependency and arc head, depending on how you look at it. So for each word, we compare it, for example, in order to calculate the score, we compare it to different words, just like transformer architecture, that you create keys and queries and values for three matrices. But here we are using just biLSTM. We are not using transformer architecture. But the idea is the same. For example, each one could be related to any other one, and we compare all of these, and finally we create this score, which is H. Because we add labels as well, so we concatenate it with the labels, and then H times U and H. So this gives you a score. But this is the arc head, but this is the arc dependencies. By H, I mean the hidden representation of your LSTM or biLSTM. Here is you're using biLSTM model. And after giving it to a multi-layer perceptron, the reason that we give it to multi-layer perceptron it is to adjust the dimensions, because once you want to calculate this H1 and H2, if you want to calculate this, then you need to adjust the dimensions in order this multiplication to be well posed. So then we calculate the scores. For example, what is this score of one arc? For example, let's see this arc. What is the score that Kim is connected to this? So for any word, we compare it to different words, and then we calculate the scores for both for everything with arc and labels. And here is good. We can see that how we use biaffine dependency label classifier, and as I said, we apply dimension reducing multi-layer perceptrons to each recurrent output vector before applying the biaffine transformation. And so these are the equations. So you see HUH, this is For any I, for any token, you get the score of that because you're creating the arc. And the arc, and of course you have some parameters to learn. These are the parameters that you should learn them by training this neural network, and then the scores can be predicted. Okay, so you see these are very beautiful equations. And so let's do it in PyTorch and implement it in PyTorch. So then the only thing that you need to know is you create a class. For example, you're using neural network. And for embedding, it doesn't matter. You could use, for example, CarolSTM, BERT embedding. You learn it end to end. You learn a simple model. If you don't have pre-trained model, let's use this one. Or you could use BERT embedding and so on. So this is just for encoding. And this is for encoding, as I said. But you give it to multi-layer perceptrons. For arc dependency, for arc head. But these two are for relations. Relation for dependency, relation for head. And after that, you combine all of them. So you say biaffine of that, and I will explain biaffine, which is really easy to implement, that matrix that I told you. So in the forward time, you're giving, first you do padded sequence. You always do that. Because the sentences are not always equal, you create some, you pack them. For example, first you pack them because, for example, you say these are batches. You should create some batches. So in each batch, the length are equal because you create some pads. If it is not okay, then these batches have the same, the sentences inside each batch has the same length. So it is necessary for any model to operate. And after that, you calculate the arc dependencies. These are multi-layer perceptrons. So X is the result of your LSTM by LSTM, but you give it to multi-layer perceptron for dimensionality reduction, for adjusting the dimension of the output. And now the loss is very simple. You just use you add the arc loss to the relation loss, and this cross entropy criterion is defined as cross entropy, the usual thing that we do in machine learning, in supervised learning, let's say. And so everything is crystal clear. And so let's talk about decoding. At the decoding step, we could use, for example, the greedy or either the beam search. So I skip it. So, sorry for breaking the silence. In future, they want to handle out-of-vocabulary tokens for richer languages, just like the idea of pointer generator network or the idea of CopyNet. And those models were created because sometimes we have out-of-vocabulary words that we just need to pass it. We just imitating, copy, and shift it. So that's why they want to enhance their model, and they will use auto vocabulary in their future article.